Here we are, chapter 7. It's the last chapter that's going to be on test 2. Okay? Now, this chapter is what I call a wind it all up chapter. It's a really good chapter, and it's going to take all of your skills. Okay? In this chapter, we're going to explore systems of interacting objects. An interaction is a mutual influence of one object on another. When two objects interact, object A exerts a force on object B, and object B exerts a force on object A. Every force, okay, is part of a two-force pair called an action-reaction pair of forces. Okay, so it's very important to remember that you can't have a force without an agent and something that's experiencing the force, but that if I push on something, okay, it's going to push back on me. So notice, I push on the wall pushes back on me. So there are two forces in the pair, they act on different objects, and they point in opposite directions. We'll formalize that in just a minute. Okay? Now, as we start to analyze systems of objects, systems of interacting objects, we want to start breaking our world into things we're interested in the motion of and things we're not. Okay? If we have more than one object in a system that we're looking at the motion of, then I'm going to be interested in those interactions between those objects and identifying how they're interacting. I'm also going to be looking at how forces from outside my system are interacting with my system or things inside my system. So we always want to be able to identify what's in the system, what's out of the system. So let's look at a couple of pictures and let's talk about what's in the system, what's out of the system, and how things are going to interact. Now, here's our first picture. A box A and a 10 Newton box, or a block A and a 10 Newton block. They're connected by a rope. So I would consider block A and the 10 Newton block to be in my system. Okay? The pulley, not going to be part of my system. This table that block A is sitting on, not part of my system. But the table interacts with block A, and the pulley interacts with the rope that connects block A and the 10 Newton block. Okay? So if we started to think about forces here, okay, about right there. Then if we have block A, okay, there's going to be a tension, T1, pulling on it. There's going to be a normal force, N1. There's going to be a force due to gravity. Okay, this is an interaction with an object outside the outside the system. This is an interaction outside the system. This is going to be an interaction inside the system. And there's probably going to be a frictional force. I'll call it F sub K. Well, I'll just use F for frictional. I don't know anything else right now. Okay? Now, if this block is going to move, it's going to have an acceleration A in this direction. We think about the 10 Newton block. Okay? It's going to have a tension T2 and a force due to gravity 2. Force due to gravity is because of the interaction with the Earth. The Earth is outside our system. Okay? This T2 is in that rope which is connected to block A. So T2, this is inside the system. So these are both inside the system. And if this guy accelerates, it'll accelerate downward like that. We go from there to free body diagrams, but we're not to that yet. I just want you to think about system not in the system. Okay? We roll on down here. we look at another picture, just kind of talk our way through it. Okay? Block A, block B, and the rope inside the system. Hand outside the system. The table that they're sitting on outside the system. The earth outside the system, because the interaction between the blocks and the earth aren't really going to change the motion of the earth, and we're not interested in those. So, let's take a moment and talk about interactions that are going to help us as we start to look at things, and namely we're going to talk about propulsion, and then we're going to talk about internal forces inside the system. Now, propulsion, is a force used to drive an object with an internal source of energy forward. When you walk, you're using propulsion. Okay? And propulsion is essentially a static frictional force. If we think about a car or a person walking, it's a different kind of force if we're talking about a rocket. Okay? But if you think about it, what you do is you push down and back with your foot. That backward push with your foot while you're walking, that pushes back on the ground, and then the ground or the earth pushes forward on you with a static frictional force. That's propulsion. Your car tires apply a static frictional force to the road, apply a force to the road going backwards, and then the car provides a static frictional force on you and your car moving forward. A rocket pushes hot gases out the back end, and then the gases push forward on the rocket. Thrust is a type of propulsion. Okay? So we're going to run into an example problem where we see propulsion. All right, now, Chapter 7 is all about solving problems with systems of objects. So there's some tools that we need to add to our physics toolbox to help us do that. The first is the third law, Newton's third law. Newton's third law says every force occurs as one member of an action-reaction pair of forces. The two member forces act on different objects. The two member forces are equal in magnitude, point in opposite directions. Okay? So this can be a really powerful tool. So if I were to say that I had floor here, and here is box A, and here is a box B, and they're sitting side by side. If I come along here and I push on box A, box A is going to push on box B. So if I were to look at just box A, there would be my push, so I'll call it FP for force push, and then it's going to experience a force from B. There's probably going to be a frictional force because if I'm pushing on it, it's going to want to move in the opposite direction. And there's a normal force on it, and there's a force due to gravity. If I look at box B, okay, it's got a normal force, I'll call it MB, force due to gravity B, okay? It's going to have a frictional force, FB, little b, and then it's going to have a force from box A. Okay? You make sure you can see all that. You can see all of it. Now, guys, if we look at this, force B and force A are an action-reaction pair. A pushes on B, B pushes back on A. Okay? That means they have to have the same magnitude, and I'll just call it F. That's what an action-reaction pair is. When two things interact and they apply forces to each other. That's the only pair of action-reaction forces in this example. Okay? We have other forces, but they're not action-reaction pairs of forces. Okay? Now, the next thing we have to talk about is an acceleration constraint, which states that objects that are attached to each other have a fixed relationship between their acceleration. Okay? Objects that are attached to each other have a fixed relationship between their acceleration. Now let's come back over here. If box A and box B maintain contact with each other, if acceleration of box A is A1, acceleration of box B is A2, I can say that the magnitude of A1 equals the magnitude of A2, and I would call it a magnitude of A. That's the acceleration constraint. Okay? Let me show you a couple other examples of an acceleration constraint. Let's say box B is a 10 kilogram box. Box A is a 5 kilogram box. And this is a frictionless table. Okay? Now, A and B are connected by a straight rope. So when I start looking at things, okay, A is going to have a tension T1. It's going to have a normal force N1, force due to gravity A, and there is no friction. It's going to have an acceleration A1 pointing in this direction. Okay? When I look at box B, it's got a tension T2, force due to gravity B. It has no friction, and we would expect it to have an acceleration A2 downward. Now, if I was to choose the wrong directions for the accelerations, the math is going to show me, okay? Now, things that I know here is because I have a straight rope, the magnitude of A1 has to equal the magnitude of A2, which I could call A. That's an acceleration constraint, okay? Now, let me show you an example that's not quite so straightforward. Let's say I have this rope tied off to a wall and it loops around a pulley connected to box A and then loops over a pulley and connects to box B. Okay? When I'm in this situation, if box B moves a foot, then box A is only going to move half a foot because of the way the rope is wrapped. That means that if I call the acceleration here of box B, it's got a tension T1 and force due to gravity B. The acceleration A2 is here. Okay? For box A, there's going to be a T1, a T2 and a T3 because the way that rope loops, it's pulling in both sections on that box. Let's say it's got a frictional force, F. It's got a normal force N, force due to gravity A. And it's going to have an acceleration A1. In this situation, A1 is going to equal 1/2 of A2. Or I could say that A2 is equal 2 times A1. We're looking at magnitudes. Okay? That's an acceleration constraint. Now, the third tool in our toolbox is the massless rope/string assumption. When a rope connects two boxes, okay, like we were looking at in the last two diagrams. When that happens, you could have the rope as a third object in your system, okay? And if that's the case, then the force at the two ends of the rope would have to be different for the rope to accelerate and the objects to accelerate. But if the rope is small in mass compared to the objects, we assume that the mass of the rope is 0. If the mass of the rope is 0, then we can say the tension at both ends of the rope is the same. And we can treat the rope as nothing but a force transfer device. This is what's referred to as the massless string assumption. Now, if the mass of the rope or cable or string is large enough, we cannot make the massless string assumption anymore, and we have to treat it as an object in our system. Okay? The last thing that we're going to add to our toolbox here is a pulley assumption. Now, when we get later chapters near the end of the semester, we'll move away from the pulley assumption. But for right now, we're going to assume that our pulley is frictionless and massless. And we make pretty good pulleys, so if the mass of the pulley is fairly small and it's got good ball bearings, making this assumption is okay. If we make this assumption that the mass of a pulley is 0 and that it is frictionless, that means that as we pass a rope over a pulley, all the pulley does is change the direction of the force, and that the tension on the two sides of the pulley are going to be the same. Okay? So let's look at our pretty problem, our pretty system over here. Okay, if we're looking at this and we're thinking about all the things that we can, I have one continuous rope. So one of the things I can say is that T1 equals T3 equals T2 equals T3 equals T1 in magnitude, and I can call it T. I'm working with the massless string assumption and the pulley assumption, because there's a pulley here and there's a pulley here. Okay? So now I have two assumptions. Well, I have two assumptions at work, and I have my acceleration constraint. And then I can start building equations, looking at the sum of the forces in the y direction on this one, then the sum of the forces in the x direction. I can look at the sum of the forces in the y direction here. I can build systems of equations that are solvable. Okay? So we're going to start looking at some homework problems. And we're going to build up. Okay? So, come back over here. And we're going to start off by looking at problem, let's see, we're going to look at problem 7. Wrong way. Okay, let's see if I can zoom this in just a little bit. Let's see. Zoom in. Wrong way. Okay, and a little more. I walked out without the stuff I wanted. Okay. Let's look at problem 7 here. Now, you're going to get a packet of solved problems to go with this. I forgot to bring them down with me right now, so we'll do a couple without me having them worked out ahead of time and on a pretty sheet of paper that I can put up there, but this will give us a start. Okay? Now, if we look at problem 7, it says a small car is pushing on a large truck. They are speeding up. Is the force on the truck on the car larger than, smaller than, or equal to the force on the truck? Well, if the small car pushes on the truck, then the truck has to push back on the small car. So that's an action-reaction pair of forces. The force of the small car on the truck and the truck on the small car have to be equal to each other. Okay, so that's not a problem, that was just a question. Now, the next thing I wanted us to look at, I'm going to ignore 3. That's just a thought problem. Let's look at problem 11. Oh, wait a minute. Wrong problem 7. There's the problem 7 I wanted to start with. Okay, let's look at problem 7 here. I like this one. Now, block B in figure 7.7 rests on a surface for which the static and kinetic coefficients of friction are 0.6 and 0.4, respectively. The ropes are massless. What is the maximum mass of block A for which the system will remain at equilibrium? Now, guys, they gave you the static coefficient, the coefficient of static friction, the coefficient of kinetic friction. I don't need the coefficient of kinetic friction. They've given us a little bit extra information. Now, if I look at this, notice there's a knot here. I'm going to make the knot part of my system. So I've got box B, the knot, and box A. I'm going to have a system of 3 objects. Okay? So the first thing that we need to do is we need to draw free body diagrams for all 3 of our objects. Okay, so box B. If I do a free body diagram here, it's going to have a normal force, N1, force due to gravity, B. There's going to be a frictional force, F sub S, and there's going to be a tension, T1. Okay? And I know that the sum of the forces in the x direction here are going to be 0. Sum of the forces in the y direction here are going to be 0 because it says box B should sit still. So the first thing you're going to do is you're going to calculate the force due to gravity. Now it's a 20 kilogram box times 9.8 gives me 196 Newton force. Okay? If we look at the sum of the forces in the y direction, and the reason I do this first is because I need the normal force to be able to calculate a frictional force. I'm going to have the normal force, N1, plus force due to gravity, B, adding up to be 0. So normal force 1 is going to be 196 newtons. F sub S, the static frictional force max, is going to be the coefficient of static friction here, which is 0.60 times 196 newtons. So 196 gives me 118 newtons. Now, sum of the forces in the x direction is going to be F sub S plus T1, and that's going to equal 0. So I have minus 118 newtons plus T1 is equal to 0. So T1 is 118 newtons. So I've got T1. Okay? Now let's think about our knot. Now, I'm going to have a tension T2 here, a tension T3 here, and a tension T4. And T4 is at 45 degrees. So T4 is going to be made up of two components. I'm going to have a T4x, which is just going to be the magnitude of T4 times the cosine of 45 degrees. And T4y in magnitude is going to be T4 sine 45 degrees. Okay? Now, I know that the magnitude of T1 has to equal the magnitude of T2 because that's one continuous rope. So I know it has a magnitude of 118 newtons. Okay? So since I know that one, I'm going to look at the sum of the forces in the x direction here on the knot. That's going to be T2 plus T4x, and that has to sum up to be 0. So I have minus 118 newtons plus T4x is equal to 0. So T4x is 118 newtons. Now I can get T. The magnitude of T is just going to be the magnitude of T4x divided by the cosine, 45 degrees. So the magnitude of T is going to be 118 divided by 45 cosine. So 167 newtons. Now, T4y is equal to T sine of 45 degrees. You do the math, you get 118 newtons. Okay? Now, I'm going to see if I can't scoot you guys over a little bit more. Okay? Going to rotate a little bit. Now we're going to look at block A. Block A has a force T5 and force due to gravity. Okay? Sum of the forces in the y direction has to equal T5 plus force due to gravity. I'll call it force due to gravity A. Now, T5 has to equal in magnitude T4y. Okay? Because of the action-reaction, well, hold on. Let me be a little bit better here. Before I go to block A, I need to finish up with the knot. If I look at the knot, okay, and I look at the sum of the forces in the y direction, I get T3 plus T4y having to equal 0. T3 then is equal to a minus 118 newtons. Now, I look at box A, the hanging box. Okay? It's got a T5 on it, and it's got a force due to gravity. The magnitude of T5 has to equal the magnitude of T3 because it's the same rope. So that's 118 newtons. So if I look at the sum of the forces in the y direction, I have T5 plus force due to gravity A equaling 0. So I have 118 newtons plus force due to gravity A equals 0. Force due to gravity A then is going to be minus 118 newtons. So force due to gravity A has to equal the mass of A times G. So I have 118 newtons equals the mass of A times 9.80 meters per second squared. So mass of object A is 118 divided by 9.80. So it's a 12.0 kilogram box or block or whatever it is. Okay? Make sure you got it all. All right. So you can see that we have to kind of step our way through it. This time I worked on B, and then I worked on the knot, and then I worked on A. Sometimes we've got to work on both of them or all of them at the same time. Okay? Now, I think I can get one more problem in before I have to go meet you guys for lab. So let's see if I can do it. Okay, let's look at problem 14. Okay, this is one of my favorites. It says, the sled dog drags sled A and B across the snow. The coefficient of friction between the sleds and the snow is 0.10. It's kinetic. He's dragging them. If the tension in rope 1 is 150 newtons, what is the tension in rope 2? The rope connected to the dog. So, we're going to assume that we have massless ropes. We don't have any pulleys to worry about here. So I'm going to have two objects, sled A and sled B. The dog is outside of what I'm considering my system. Okay? So let's start doing some free body diagrams. A, B. Now you'll see when you look at the problems that I'm giving you, I usually split that page in half, at least halfway down. Okay? Things I know here is the mass of this sled is 100 kilograms. That means the force due to gravity on it is going to be 980 newtons. Okay? Mass of B here is 80 kilograms. Force due to gravity B then is going to be 80 times 9.80. So that's 784 newtons. Now, if I look at this sled A, it's got a normal force, I'll call it N1, force due to gravity A. It's going to have a frictional force, I'll call it F1, and then it has a tension T1. Okay? And it's going to accelerate, if it accelerates in this direction, A1. Okay? Now, I'm going to go ahead and do the sum of the forces in the y direction. That's going to be the normal force plus force due to gravity A. Should add up to be 0. So the normal force here is going to be 980 newtons. Our frictional force is going to be the coefficient of friction, 0.10 times 980 newtons, so 98.0 newtons. And that's its magnitude. We look at the sum of the forces in the x direction. I have T1 plus F1 has to equal the magnitude of the mass of A times A1. So I have T1 being given to us as 150 newtons. So T1 had a magnitude of 150 newtons. So I have 150 newtons plus a minus 98.0 newtons has to equal 100 kilograms times A1. So I've got one equation and one unknown, it's solvable. 150 minus 98 divided by 100, I get A1 to be a plus 0.52 meters per second squared. That's everything I can do with sled 1. Now let's look at sled 2. There's going to be a frictional force, I'll call it F2. there is going to be a tension T2 here. Well, I'll call it T3. T2 I'll leave in rope 2. There's going to be a normal force N2 and a force due to gravity B. Okay? I'm going to do the sum of forces in the y direction first because I need to calculate a frictional force. So, force due to gravity B plus the normal force has to add up to be 0. So the normal force ends up being 784 newtons. So F sub s here, the frictional force 2 in magnitude is 0.10 times 784 newtons. That gives me 78.4 newtons as a magnitude. Okay? Now other things we know. The magnitude of T3 has to equal the magnitude of T1, which is 150 newtons, because it's one rope. Okay? And I know that the acceleration of this sled, A2, has to equal in magnitude the acceleration of A1, which we know is 0.52 meters per second squared. Acceleration constraint. Okay? So now let's look at the sum of the forces in the x direction. So I have T2 plus T3 plus frictional force 2 has to equal the mass of B times the acceleration A2. So T2, I don't know. T3 has a magnitude of 150 newtons and it points backwards. The frictional force we got is 78.4 newtons and it's pointing in the negative direction. And that has to equal the mass, 80 kilograms, times 0.52 meters per second squared. So I have T2 minus 228.4 newtons has to equal 80 times 0.52, 41.6 newtons. So adding over, I get 270 newtons. And it's positive, which is what we expected because we expect things to be moving in the positive direction, and I would have to have a net force in the positive direction. T2's got to be in the positive. Okay, make sure that you can see all of that. Okay. Now, that's where I'm going to stop it so that I don't run out of time before lab tonight. I'm going to work 3 or 4 more problems for you out of chapter 7, just so you start to get the rhythm of how these problems work. Okay, here we go.